Hello everyone, welcome back to the lecture series on computer vision. This is Sainath Chaitanya, Assistant Professor from Department of ECE. We are in the track of image segmentation. In the earlier sessions, we studied about image segmentation process on similarity based. Like, we gained knowledge on how the threshold and region growing, splitting and merging plays a role in the segmentation process, and also how the active counter watershed techniques participate in this process of image segmentation. Apart from all these things, we also have got certain awareness on the machine learning techniques, in fact, k-means and mean shift, and their involvement also in the segmentation process. So all the techniques are completely based on the similarity based. Now here we are left to discuss about the discontinuity based segmentation process. Like, we need to discuss about the point detection, line detection as well as the edge detection techniques inside it. So let's move forward ahead here. We can see how we have to know how to detect an isolated point in an image here. So detection of isolated point. So this isolated point pixel intensity level is quite different, in fact very sharp. Like, if I have provided you with an image, so in that image or inside that image there will be a point whose intensity is very quite different and it will be sharp. So how to detect that kind of a scenario we need to discuss here. So this, let it be a input image that I was being provided here with, and I do have here a mask which is of 3x3 matrix mask. This is, so this 3x3 mask is applied to this input image such that I can able to detect where the point is present, where that isolated point is present inside an image. So how the process involves here. So let me take a 3x3 mask, that is my 3x3 mask, -1 -1 -1 -1 8 -1 -1 -1 -1. So let it be considered as a 3x3 mask here. So this mask is being convoluted with the input image. As you people know how to do the image convolution operations. So after applying the convolution or after applying the mask to this given input image, we are getting a product that is in this manner. So output after applying the mask will be this kind of a matrix. Because why I am considering this as a matrix means, so the input image is in a matrix form, okay, and the mask what we have taken here is also in a matrix form. The output also definitely will result in a matrix form. So where, at which location I can consider that an isolated point has been detected is, so this mask is applied to this input image, right? Because you can see at all the locations W1 to W9 we are having a value of -1, except at W5, that is having a value of 8 here, you can see. Now this is convoluted with this input image. Finally I am going to obtain this as my output. So at which location I can able to trace out that and point, a sharp point is present inside my image. So we say that an isolated point has been detected if there is a condition. What is that condition? That is 8 into f5. So 8f5 minus sum of the all pixel intensity values. So minus f1 plus f2 plus f3 plus f4 plus f6 plus f7 plus f8 plus f9. If this entire expression is greater than some threshold, so this threshold is some positive value which is already pre-specified. So if this expression result is greater than the pre-specified positive threshold value, I can say that a isolated point has been detected. So you can see in this slide a turbine blade image. So this is where at this point which is wrapped by a orange color circle. So at this point I can consider some sudden sharpness or high intensity is present at this area, right? That means in this region at some point I can feel certain high intensity value. So that means it is some point, isolated point. I need to diagnose at which location. So what I will be doing, this is the input image that is being provided to me. I will be applying certain mask to this input image, and the result of my operation will be this one. The result of, so where I will be able to diagnose where the point is, right? So after that one, still if I want to have a better result, because I cannot say this is like a black and white image, right? So still if I would like to have a better result, what I will be doing, I simply apply some kind of a thresholding. So the result of thresholding will be here, where at this location I can feel a point. So this point is bit brighter when compared to the remaining pixels, because remaining pixels I can consider it is black pixels and this point is some kind of a white pixel. So we decide this threshold, that is whose value is that means any pixel in this image whose value is larger than the threshold T after being masked will be considered it as an isolated point. So this will be my isolated point here. So the pre-specified threshold, we should be cautious on this one. And also we can use the second order derivative. Of course it is nothing but it is a Laplacian. So this is f of x comma y, this is my function f of x comma y. So where that means in an image we do have x coordinate as well as the y coordinate. F of xy represents, it is the intensity value or the grayscale value at each and every pixel location. So second order derivative, this one is very sensitive to sudden changes. Okay, it is aware of thing, and which also can be used to detect an isolated point. Okay, so this second order derivative is also called as a Laplacian. So this is my Laplacian operator. So for this Laplacian operator, the corresponding mask will be like this: 0, -1, 0, -1, 4, -1, 0, -1, 0. Again it is a 3 by 3 matrix. Like the mask will be of different kinds, like here it is a certain mask and here also it is different, some different mask. This is for Laplacian mask it is. So this is the property of a Laplacian mask. Okay, and so del square f of x comma y equal to, I can write this Laplacian operator, I can represent this operator in terms of by dou x square by dou y square. Right, so dou square f by dou x square can be represented in the finite discrete equation in this manner. Similarly, the dou square y by dou square f by dou y square can also be represented in the discrete equation in this manner. So how these two equations are obtained, let us discuss now. So discrete approximation. So what are these discrete approximation? I have two axes. In a two-dimensional coordinate system, I am having x-axis as well as the y-axis. So let me use the variable, or let me label the x-axis with x only, and let me use f as the label for the y-axis. So here I will be having a location that is x, and there is one more point here, that is dx difference before it, and there is a one more point dx with dx difference after it. One is beyond it, one is behind it. Okay, so what is this finite difference profile? Now backward difference. So with whom I have to perform the backward difference? So I assume 2 points here. One point is located at x plus dx and one point is located at x. So what is this backward difference is nothing but, of course, this point is and this point, they are like separated with dx of distance. So df by dx equal to, so what is this point? the magnitude at this point is f of x plus dx, and the magnitude at this point at this curve is, you can see here there are red line, green line as well as brown line. So apart from it, I do have a curve or a curvature which is in violet color, you can feel. So at this point, that is x plus dx, its value is f of x plus dx, some value, okay, and at x my magnitude at this point x is f of x. So I need to find out the backward difference, that is backward difference df by dx equal to f of x plus dx minus f of x by what is the separation between these 2 points, that are dx. Similarly, forward difference. So what is this forward difference? So df by dx equal to f of x, that means this point, minus f of x minus dx. So the magnitude at this point is f of x minus dx by dx. So this is my forward difference and this is my backward difference. So forward difference is given with this line and backward difference is given with this line, right? Now finally, what by using these assumptions I can able to find out my second order derivative. So this is a first order derivative and this is my second order derivative, that is d square f by dx square, can be written like this. Second order derivative means twice dx, because second order derivative twice of dx, that is dx square. So from that means I can come to a conclusion that it is a difference of this point with this point, right? Dx square. That means f of x plus dx minus f of x minus of f of x minus f of x minus dx. That means what here I am doing, I am just backward difference minus forward difference I am just doing actually here. This backward difference equation is this one, this forward difference equation is this one, truly speaking. So forward difference minus backward difference will be giving me the second order derivative, that is d square f by dx square equal to forward difference, that means this one minus the backward difference is this one. Finally I can able to obtain the second order derivative in terms of this expression. So this is about discrete approximation representation for this d square f by dx square. Similarly, at a glance I would like to show you the first order as well as the second order derivatives in the discrete approximations. You can feel here df by dx is nothing but f of x plus dx comma y minus f of x comma y by dx. So assume this is my reference point which is located at x comma y location in the image. So if I move towards one box left side means, that means I am moving towards left side 1 pixel. If I move right side means I am making a difference and moving forward right side 1 pixel difference. So assuming each and every pixel center is separated with 1 unit distance, that means this pixel to this pixel is separated with 1 unit distance and this pixel to this pixel location are separated with 1 unit distance. Similarly for my top pixel as well as with my bottom pixel. So if this is in two-dimensional coordinate system, the forward difference is dx and the backward difference with reference to the center pixel is minus dx, and the forward pixel with reference to the center pixel is plus dy and with reference to bottom it is minus dy, right? So now df with respect to x, that means along the x-axis, right? Forward difference is how much? I can feel f of x plus dx comma y minus f of x comma y, and still I can able to write the forward difference in this manner, that is f of x plus dx comma y minus f of x minus dx comma y with respect to dx, because from here to here right? Df by dx, it is with respect to single x. If I would like to find out for twice, that means from here this pixel to this pixel, if I would like to trace out the if I would like to find out the first order derivative with respect to x, so previously this equation is for this one with this one. Now df by dx I am finding out with respect to this pixel to this pixel, left pixel to right pixel. Okay, so that means f of x plus dx comma y minus f of x minus dx comma y by twice the difference, because from here to here the difference is dx, from here to here also the difference is dx, so by twice the difference. So I can able to write the first order derivative either by using this expression, or I can still use this as a representation. The same thing I can even apply for the y-axis. That means like the difference along the y-axis of the 2D coordinate system. So where in the previous case dx is my variable, okay, and now at this present case dy will be variable, because I am considering here these three pixels, center pixel, top pixel as well as the bottom pixel. So the center pixel is like separated with top and bottom pixels with a discriminate value, that is dy, right? So finally dou square f by dou x square can be written as forward difference, that is if I consider dx value, that means separation between any two pixels, as unit distance, just replace dx with 1 and dy also with 1. Now f of x plus 1 comma y minus 2 f of x comma y plus f of x minus y comma y, x minus 1 comma y by dx square. Now you may ask me how I have written this equation directly, because this is my 2D profile. In my previous slide I have shown you the 1D profile. These are the 1D profile finite difference approximations, discrete approximations. Like, because I don't have any y coordinate here, I have considered only one coordinate, that is x, and its a magnitude, that is f, because it is a signal. It is some curve is there, right, which is in violet color, it is some signal, right? So second order derivative, how I have explained you, like I have used here one variable in the argument. Similarly in the 2D profile I have to use one more extra variable, that is y variable. Finally I am going to obtain my 2D profile for the finite difference approximations in this manner. So let's come back here. Now I do have a Laplacian mask in this manner. This Laplacian equation, that is del square f of x comma y equal to dou square f by dou x square plus dou square f by dou y square, which is represented in this 2D profile of finite difference equations like this. Finally I can write this del square f of x comma y is a summation of this equation plus this equation. Ultimately I am getting the same value here, that is f of x plus 1 comma y plus f of x minus 1 comma y plus f of x comma y plus 1 plus f of x comma y minus 1 minus 4 times of f of x comma y. So this equation is also helpful for me to find out the isolated point in the image. Why? Because this equation is resembling me the same, right? Like f5 minus the summation of all these pixel values is, if it is greater than the threshold, I can detect a point in the image. The same thing. So this equation also resembling me the same kind of picture, right? So this del square f of x comma y and the corresponding mask is this one I have said you, and the equation that I have obtained is this one I derived. But is there any correlation between this equation and this mask? Definitely yes, some kind of relation is there. Like if this is my central pixel value, that is f of x comma y, so what it will be, it is f of x minus 1 comma y, this will be f of x comma x plus 1 comma y, right? And this will be f of x comma y plus 1, and this is f of x comma y minus 1. So if I add all these things, ultimately I will be getting this as the resultant equation. So del square f of x comma y is represented in this 2D profile of finite difference approximation. So this is the way how one can able to detect a isolated point in the image. Now let us see about how to detect lines. If any lines are present in a given input image, how to detect or diagnose a line, whether it is truly present in the input image or not. As we know that Laplacian is responsible for sudden fluctuations in the intensities. So Laplacian is sensitive to sudden changes. So where I can now employ this Laplacian in the detection of lines also. So like there will be some masks which are helpful to detect the lines which are present in certain directions in the given input image. Like if we would like to detect lines on a certain direction, we use certain mask that will detect the lines whether they are present in certain directions. So those masks here are, for an example, I take into consideration Kirch compass operators. So these Kirch masks. So how these Kirch masks are helpful in detection of lines, we will discuss now. Like these Kirch mask offers or comes up with 8 masks which are separated at 45 degrees angle. So if I am having a 360 degrees, so if I divide the 360 degrees by 8, I will be getting 45 degrees, right? So that means I can able to get here, or the Kirch compass operator is providing me the 8 different masks. So these operators are used to detect the lines which are oriented at interval of 45 degrees in the image. Now out of the all 8 masks, we no need to use here all the 8 masks. We can use any of the 4 masks. So these 4 masks are convoluted with a given input image, and we get the resultant output image such that it is like able to detect the any lines are present in those 8 directions, right? So then what about the remaining 4 masks? Of course, the remaining 4 masks produces the equivalent result with reverse sign. That makes it different. That means it is not a huge difference here except a sign reversal. So if I consider f of x comma y as my input image, and some, as I have said you, there are 8 masks that are provided by this compass operator, that is Kirch compass operator. Let it be h0, h1, h2, h3, h4, h5, h6, h7. So h4 and h0, they resemble the same one. Okay, so how it is, I will show you in the next slide. Now this is my Kirch compass operator. Each and every mask is separated with 45 degrees angle. Like for example, if this is my original mask, okay, so that means if I do a 45 degrees rotation, I will be getting this is the resultant mask. Still, if I do a 45 degrees rotation, so I will be getting the resultant mask in this manner. So this is my 0 degrees mask, 45 degrees mask, this is my 90 degrees, this is my 135, 180, 225, 270, and so in this manner it goes on, right? Now this mask is used to detect a horizontal line. This mask is used to detect a vertical line, and this mask is used to detect a northwest or southeast lines in an image. And these 2 masks, like this one as well as this one, can able to detect a north, east or a southwest lines in an image. So as I have said you, if this is my H0, right? So H0, this is my H1, H2, H3, H4, H5, H6, H7. It need not be H0. I can consider this one as also as an H0. Okay. So this H0, right? This H0 and this H4, because H0, H1, H2, H3, H4. So this mask and this mask, they are alike in magnitude but reverse in sign. So here -1, -2, -1. I have here 1, 2, 1. Here 2, 1, 1. Here -2, -1, -1. That means this H0 as well as the H4 mask are similar in magnitude but reverse in sign. So that is what I have represented here. So once any of the mask is convolved with the input image, I can able to diagnose where the line is present in the given input image, and also I can comment on, that means at that particular point which line is passing, right? So at that particular point, which, if it is a 45 degrees line or if it is a 90 degrees vertical line or it is a 135 degrees line, which line is also passing, I can also give that result also. I can also find out the result also. So it all depends upon the mask what we are applying here. So this is what, like for example, if I apply this mask to my input image, and at the particular pixel location in the input image, if I trace it out with a line, that means this is my 45 degrees line is passing through that particular point in the image. So this what I can conclude. So you can see here, this is my original input image. So I have indicated some red color dot here, as well as here you can see. So R0 is nothing but it is the resultant image. That means it is nothing but this image is obtained after the convolution of the mask with this input image. So R0, let me assume, so this mask, whenever it is convolved with your input image, I will be getting R0, and this mask, whenever it is convolved with your input image, I will be getting R1. This is R2, this is R3, right? So R0 equal to maximum of, so at this particular pixel location, okay, I am applying a 0 degrees mask, 45 degrees mask, 90 degrees mask as well as 135 degrees mask. So for this input image, now I will be getting R0, R45, R90, R185. Among these all the resultant images, okay, so like R0, R45, R90 and R185 will be having its respective matrix values at this pixel location, right? So among this pixel location, among the resultant mask at this corresponding pixel location, whoever the resultant is having the highest value at this point, I can conclude that particular line is passing through that pixel. Like, let me explain it you clearly. So take this example, take this image, this resultant image as an example. I have a point here. So some line is passing through this point. I don't know what exactly the line is at this location or at this mark, red mark. What I have done, basically I just applied the 4 mask, like 0 degrees, 45 degrees, 90 and 135 degrees mask. I have just applied as an I have done the convolution with this input image. Okay, now I have got four different masks, right? So 4 different results which are in matrix form. Okay, now I want to find out which line is passing through this point. That means I have to check with the results of 0 degrees mask, that is R0. I have to check with the result of 45 degrees mask, 90 degrees mask, 135 degrees mask. So whenever all these masks are convolved with the input image, I will be getting the result as R0, R45, R90 and R135, which are nothing but are the responses for the mask H0, H45, H90 and H135. H given pixel location, that is x comma y. This is x comma y. So among these, I figured it out that a 135, that means R135 is having the highest value among all these resultant, among all the results, right? So that means I can conclude that a 135 degrees line is passing through that pixel. So that means if R is the maximum among R0, R45, R90, R135, at this point R135 degrees line is passing through that pixel. So in this manner I can figure it out. A particular line will be passing through a particular location in the given input image. So you can see here a 90 degrees line is passing here at this pixel, and coming to here a 45 degrees line is passing at this point in the image, resultant image, and at this resultant image a 0 degrees line is passing. So this is the way how the Kirchhoff compass operator can be helpful for detection of the lines in the images. So the same thing you can hear. So sometimes what happens, if any line is not present in any of the 8 direction, where the Kirchhoff compass operator definitely fails. So at that point of time, we have to go with the directional transformation. In fact, Hub transformations are highly helpful and definitely will come into the picture. So we will discuss about these Hub transformations in the upcoming sessions. Thank you.